from the University of Chicago, and he's going to talk about homogenization in random environments.
Thank you very much. Good morning. I'd like to thank my co-organizers for giving me the opportunity to give a talk. You know, it's always nice when you are in an organizing committee to have someone who is able to do everything, and or at least two. So I'd like to thank in particular Michael for finding some of the funds that paid for some of us to be here, and also for Zitzler, because without him there wouldn't have been a program and there wouldn't have been a workshop. So it was very nice to have someone who took care of everything. All right, so I changed my title because I want to give you an overview about something that I don't think has been talked about either in the conference or even I think in the whole program. And when we had the program, so I like to give you an overview of some area of research that I've been involved the last number of years, which has to do with homogenization in random environments for degenerate elliptic PDEs. So this is a transparency. I always put it up there because I try to find a definition of what homogenization is. I think everybody understands what homogenization is, but if it's hard to find somewhere written what it is, I went to Wikipedia and blame Wikipedia for that. So when we say something homogenizes, what we have in mind is we have many different scales, parameters, and somehow we average over them. And if we have equations, we do the same problem. We have an equation that depends on many parameters, and we want to find what is the average thing. So the kind of equation I'm going to deal with, okay, are second order. I'm writing in the simplest possible way to save space. So I will be interested either the problems without this term or the problems with this term but not that. Scaling doesn't allow me to handle both of them. So either they are elliptic or there is an epsilon in front of the second derivative. And the questions I want to ask is whether we can have, it will be random, but I'll come in a minute back and say what omega means there. So what we want to know is whether we have a limit along the whole family, whether the limit satisfies some universal translation invariant equation. And again, if there was a d square u epsilon there will be a d square u bar here. If it isn't, there is none. Whether there is a relationship between f and f bar, whether we can find rates of convergence. And since I promised to talk about random homogenization, whether there is really any difference, any qualitative difference between random and periodic. I mean, there are a lot of technical differences, but I want to see whether there are any qualitative. All right, so this is now a sequence of transparencies which show possible applications of the whole thing. So this one is a simple level set PDE, like the Econal equation, which basically is the simplest equation you can have when you try to find geodesics, connecting points in environments with bumps or whatever. This is a little bit more sophisticated in the sense that I put a time derivative in front, and this is the level set PDE that describes the evolution of a front, let's say with normal velocity 1 if you are in the gray region, 10 if you are outside. Okay, the picture here doesn't really mean that. And always the way I think of that is that you are far away, you don't see all these wiggles there, but you see some nice curve, and the issue is how you can justify that. Let me give you two more sophisticated examples. So the first one is what is known as the G equation. So the G equation, think of it like that. G equation is this. And it is the canonical model people use, engineers use in turbulent in combustion to describe the motion of a front, of let's say the fire going through. And then they call it turbulent if they add to this an advection term. And then they are interested in understanding what happens as epsilon goes to 0. So schematically, the picture is you have a front, a sharp front, that is moving with normal velocity 1. Then you advect it, for example, with this vector field v. This thing starts getting oscillatory, and then you let epsilon to 0, and you get some effective front. And the question they're asking is, first of all, whether there is a limit, and number two, whether you have an enhancement. Namely, whether the fact that you start messing around with a sharp front, whether it makes it go faster than before. Now, this in principle, in my opinion, is not a very realistic model because, as I said, you start from here, and that assumes that the reaction has taken place. So like saying, it's like having a situation where you have a fire going through a forest, and it's a very clear, sharp boundary between burned and unburned. And that's not really the case. So if you want to see a little bit more sophisticated model, is a model where now you are at the level of the reaction taking place. You advect, and then of course you have some diffusion. So this is the situation where, if you like, you have the burned region here, there is the unburned region, and there is a front of thickness epsilon where everything is taking place, which is a little bit more realistic. So again, you can ask similar questions, and you can also homogenize this problem, and that's related to possible random traveling waves, the speed of possible random traveling waves for KPP equations, which of course don't exist. Another example is, this I'm not going to spend much time, is large deviations in a random environment, where now you have diffusion, and there is the coefficients random with respect to a different probability measure, and you ask the typical large deviations question. So something like that, you can translate it into a homogenization problem. This is maybe a little bit more, when I see that in my laptop, I don't know. Anyway, so this is a related problem, but written in a different way. So suppose you have the semi-linear heat equation. You start with velocity 1. I mean, you start at 1. Of course, the solution is given by Feynman cards like that. And what you do is you are interested in the long-time behavior of the solution. So what happens as t goes to infinity? Now, we know that that is related, at least if we are in a periodic environment. This is related to the principal eigenvalue of Laplacian minus Laplacian plus v. In particular, in the periodic setting, one can prove this result, that logarithm of uxt over t divided by t converges to the minus the principal eigenvalue. And the question you would like to ask is, what happens now if the potential is random? If you are interested in such kind of questions, there's this wonderful book by Schnittmann on I think Brownian motion or obstacles and random media, and you can have a whole book where you ask, you study questions like that. It turns out that's very much related to homogenization, because if I rescale this problem and use 1 over epsilon and 1 over epsilon there, then I get a homogenization problem, which is like u epsilon t minus epsilon Laplacian u epsilon plus 1 over epsilon vx over epsilon omega. So it's the same behavior. Okay, now I'm going fast because I don't think I will finish in my 50 minutes, whatever I have prepared. So I'd rather give you a panorama, and if anybody is really interested, I can go back and explain things. So these are the two pictures I like to show when I talk about the kind of environments we have in mind. So I group them like that. First is periodic, almost periodic. That's clearly some kind of a periodic situation. And this is, I don't know why, this is an almost periodic environment. So that's again stealing from Wikipedia. This is a Penrose style. And you read that these are almost periodic. Okay, so I show you these two examples. It's very difficult to draw one. And then here the random, and I present 3 types of random environments. And again, this is just a realization. So here is a regular chessboard, but what is random is whether you leave it white or you make it gray. So at each box you flip a coin. The second is what is called spherical inclusions, and it's a capture of the Poisson potential situation. So here what you have is you have balls that have radius 1 at scale 1, and what is random is the center of the ball. So these are distributed, let's say, with some Poisson distribution. And this is a more dramatic example because you have 2 randomness. One thing is whether it's white or gray, and the other is the size of the rectangles. So you can have arbitrarily small and arbitrarily large rectangles with the right probability. You can have an example like that also, where you can have clusters of things like that. So you can think of some random distributions of random points, and you can have clusters that are distributed randomly. So the reason I'm putting them like that is that there is a fundamental analytic difference between periodic, almost periodic, and random. So in some sense, periodic is compact, while the general random setting is not compact, and that creates tremendous mathematical difficulties to study the homogenization. More or less, you have to do something completely different to do the second. All right, now let me explain heuristically what I mean by the picture I have in my mind. So the picture I have in my mind is that omega, the probability space, are all equations. So little omega denotes F. So I have all equations, so I have a big bag with all the equations, and then I assign some probability to pick up equations subfamily, and in my case will be equations which share some common properties. For example, if they're uniformly elliptic, their constants are bounded, uniformly bounded, the ellipsis continuous, and so on. So I have a probability measure that distinguishes certain kinds of equations. And then I want to define some kind of process that will allow me to average. So the first property is a stationarity. And for me, stationarity means that, let's say now change instead of a bag, I have the equations behind the blackboard. I open a window here. I see a bunch of equations with some probability. Then I go to that blackboard. I open again a window. And what I see is with the same probability the translations of the equations that were here. So the fact I said, so equations from there are translated to equations here, so that means there is a transformation that takes something there to here. That's a transformation from omega into omega, because remember the equations are elements of omega, and I mentioned the same probability, so the transformation has to be measure preserving. And so the idea is that equations translated by y are nothing else but the translations of the equations that I saw before. So that's stationarity. And but that is not enough to homogenize. What you need to do is you need to make an additional assumption. Then let's say the most one of the close to general you can make is ergodicity. So you want the equations to translate themselves, and the way I think about that is let's go again through this example of opening windows. I open a window there, then I open a window here. I keep opening windows, and by the time I finish, I have seen all the equations. And one way to state that is that if you start with a set of positive probability and you build out of that the largest possible invariant set, that's everything. Okay, so that's the ergodicity. So here's the heuristic idea. I have, let's say, equations which they have the same frequency no matter where they are. That's the stationarity. And let's assume that I have two kinds of equations. They are blue and red. So if I don't assume anything else, in the end, I may continue seeing only blues or reds. But if I put some mixing, which is the ergodicity, in this case, then at the end, I may get something that is uniformly purple, for example. And if I put a rate on the mixing, then I may have some hope to see how many solutions are close to the averaged one. So the idea of random homogenization is you homogenize over all possible equations. Now let's compare that to periodic homogenization. Periodic homogenization, you have one function, and that's it. Now how do you embed it on this problem? You have your function and the translations of the function. So because it's periodic, all the translations, you translate by elements in the unit cube, let's say, and then you identify your translations with the unit cube, and that's the compactness I was talking about. If you have almost periodic, you have again one function, and the definition I'm using for almost periodicity is that you have uniform limits along subsequences going to infinity. So you take your almost periodic function, you add to that all the possible limits at infinity, that makes some kind of a compact space, you define some kind of Haar measure on that, and that's again the compactness I was talking about. Nothing like that will work in the random setting. Okay, so this is just to make what I said before rigorous. So probability space, a measure preserving transformation. This is the definition of a stationary function. I repeat what ergodicity is. And for later use, I want to just say what I mean by strongly mixing, so or mixing here. So the intuitive idea is that the equations that are moving further and further apart decorrelate. Okay, so if you have an equation here and an equation really far away, they don't see each other. Of course, this is not 100% accurate. What you need to do is you have to create some sigma algebras with C equations in some certain location and some sigma algebra seeing equations further away. And what you are asking is that this probability, this expression here, to have some decay. All right, so this is soup over A. Yeah. All right, so, but the intuitive idea is things that are far apart decorrelate, are independent. I keep that in mind because at some point I'm going to say strongly mixing. All right, there are, of course, now I'm speaking to the people who know that. we're going to have to use two tools. One is the ergodic theorem, and the other is the Sabatier-ergodic theorem. Let me stick on that because I may have time to discuss at the end an example where the assumptions of the Sabatier-ergodic theorem don't hold. So this is, let's say, we have a discrete situation. We have something that is a sequence that is integrable. Here I combine subadditivity and stationarity. So when you are at g at n plus m, you are below g n at omega plus g m translated by n. And then, of course, you have long time average limit. And the key thing I want you to remember here is that I need this assumption, the integrability. And the reason is that at some point I will state a result where we don't have that. Okay, now that's for the fun of it. This is an observation that, you know, when you learn a subject, sometimes you come across some things that you didn't believe, that you didn't expect to be true. So you make a big deal out of them. For most of you, may be a triviality, but nevertheless, for me, it's a big deal. So I like to present it in lectures. And I have the following made-up situation. I have, let's say I have a stationary family of functions, which are, let's say, Lipschitz continuous. The assumptions are because I need it in a particular setting. But let's say these functions are Lipschitz continuous with constants that grow like delta. Right? And let's say I know that at the origin, I have a limit. So stationary family, Lipschitz continuous with constant like delta, and I know that at the origin they have a limit. And the question is, can I extend the limit at the origin to a limit in a bigger set? Now, it doesn't take much to see that if you use balls of radius little of delta, if you have convergence at the origin and your functions have I didn't mean 1 over delta. I mean there, okay? That will be too easy. So if I have here little of 1 over delta, then I have uniform convergence in such balls automatically. The question is, do I want to go further? And I would like to go further because remember, I'm doing all this scaling, so I'm always working at x over epsilon times epsilon. So the real question is, can you really say that the convergence goes up to balls of radius 1 over delta? Can you reach the limit? And that's for a PDE statement, it's a hard statement. I don't know how to prove most of these things with PDE because this is exactly at the point where the Lipschitz bound kills the radius of the ball, and you need something else. It cannot be a Lipschitz estimate. And that's where the ergodic theorem comes in here and tells us that indeed, we have if you have convergence at the origin, then we have almost sure convergence if balls of radius 1 over delta. And let me describe the heuristic argument, which of course is not true, because what is behind is basically sets of measure 0 in some sense. Because what does it mean you have convergence at the origin almost surely? It means that you have some subset of probability 1 where you have everywhere convergence. Then you look at W delta x of omega. By stationarity is W delta 0 tau x of omega. And if the tau x of omega happen to be in the omega 0, you are done. So convergence at the origin implies convergence for every axis that drive any arbitrary omega into the good set. So now that's an issue of measure 0, okay? You have a measure preserving transformation, and you want to find all the omegas all the x's that drive an arbitrary omega into your good set. If you think about this, is almost like a situation of measure 0, but that comes back, ergodicity should help you, but that comes back to this property about the ergodicity that you have to start with something at probability positive. So, so the point is that you expect that as delta goes to 0, tau x over delta of omega will fill everything, and it turns out to be true only if you take x to be in balls of radius 1 over delta. So let me show you why something like that is true. And so this is a general statement, how to use the ergodic theorem in such kind of situations. So suppose you have a good set. You have some set E in a subset of omega, the probability space, which is good. I mean, the property you like holds on that set, and of course that set has positive probability. Then you define as E of omega the subset of Rd that omega now is given any omega. You define E of omega the points x in Rd that drive that omega into your good set. Okay, there's a good set, and for every omega, I call E of omega all the x's such that a tau x of omega is in the good set. And you are interested in figuring out how large is the set E of omega. And so here's what happens. The ergodic theorem tells you that almost surely, and here I'm cheating again because there are sets, I mean, I have to do it along subsequences and so on, and then put all the subsequences together. Anyway, the ergodic theorem tells me that the measure of this good E of omega intersection of the ball can be estimated from below in terms of the size of the ball. And how is it estimated below by the size, I'm sorry, not the size of the ball, by the probability of the good set? Because the ergodic theorem says exactly this. And so, which means that basically, almost surely, the intersection between the set E of omega and the ball of radius r divided by r, I have to divide by b of r, the measure of that is a portion of PE. So in particular, if you are in a situation, so think what that means. It means that for every z in the ball of this is divided, I should have multiplied here by measure of br. So that means that for every z in the ball of radius r, I can find, and almost surely I can find some y such that tau of y is in E, and the distance is some multiple of the radius. And if you knew that theta is near 0, which will be the situation where if the probability of V is 1, then that is what allows you to prove what I mentioned before. So think this as a general argument. A good set, you can say something about the x's that drive any omega into the good set. And that's what is behind the theorem, the observation I made before. Okay. From the point of view of studying the homogenization, at the technical level, what is the difference between random and periodic? So in other words, how do you quantify this point I made about compact and non-compact? If you are in the periodic setting, you have all the Sobolev embeddings, you have isoperimetric inequalities, you have whatever you want. If you go to the abstract space, you lose that. Now, what is a Sobolev space in omega? A Sobolev space in omega is you have L2 of omega. The measure presenting transformation is a unitary operator, so you can define the generator of translations in every direction. So that's some kind of a derivative. So you can define H1 of omega and so on. And you ask the question, is H1 of omega compactly embedded in L2? And the answer is no. And that kills everything in terms of PDE. There is no isoperimetric inequality. How do you prove any of these things, by the way? The way you prove any of these, all these embeddings or the attempt to do embeddings, you do it in bigger and bigger balls, and you let the size of the ball go to infinity, and you try to use the ergodic theorem again and again. So if you try to do isoperimetric inequality, of course, in every big ball, you have an isoperimetric inequality, but the constant as r goes to infinity will go to 0, so you lose it. This doesn't mean there are no random environments for which you can have isoperimetric inequality, but remember, I just want to do in a general setting. And why I talk about isoperimetric inequality, because if time allows me, you're going to see that it comes up in a situation. The simpler problem, which at least at the level of homogenization creates... Yes?
I mean, this part I didn't understand. Where is the isoperimetric inequality? What problem are you?
Because the only way, because number one, it's not true in general. I don't know the counterexamples, but the way it fails...
I mean, what's the statement which is not true or true?
Wait till we get there. A way to describe it is take the classical isoperimetric equality in a ball of radius r. Okay, take that estimate.
You mean the one depending really for
Take a big ball.
and in this ball you take a set?
Yeah, and you do the usual isoperimetric inequality, so there is a constant in front. But the isoperimetric inequality that, I don't assume periodicity or anything, isoperimetric inequality that corresponds to that ball. And that constant, as r goes, when you do the average, as r goes to infinity, that constant will go to 0. We'll do it later. I mean, we can do it later. You'll see. I mean, I'm not going to show it, but let's discuss that later. Where am I? Here. So at the technical level, I would say the most complicated point in this homogenization, this stupid example. Of course, not in 1D. So you have a periodic function, it has mean 0, you integrate it, and you get a periodic function. So I claim stationarity is extension of periodicity. So now I ask the same question. Take a stationary function that has mean 0, integrate it. Do you get a stationary function? And the answer, of course, is no. What you get is a function that is strictly sublinear at infinity. So the function can grow. And that's a problem in the homogenization. That's exactly the technical problem you have, which cannot justify. And that's, of course, a consequence of the ergodic theorem. So remember that property, that things have to be strictly sublinear at infinity. I don't mean that there are no stationary functions that if you integrate their gradient, you get something stationary. I'm just saying, again, in general. All right. The thing that can go as the references. I have made sure that everybody in this room is in this reference. So if you check the transparencies, you are there. So now I want to give you a bunch. I want to describe. But that's why I'm not signing the piece of paper that says that they can tape me. All right. So now I'm going to give you a bunch of results, and I start with the first this case where I had f of epsilon d square u epsilon, and so I'm writing now results that one can prove. So think of the following class of equations. So I have epsilon, the trace of some oscillatory matrix, plus h of du epsilon x over epsilon omega. So that will cover the case of large deviations, and you will cover the case of the asymptotic behavior of the semilinear heat equation. All the time I'm writing things, I'm going to assume that I have stationary ergodics. Anytime there is omega stationary ergodic. And I'm going to assume A can be degenerate elliptic, and H has to be coercive. Coercive means that if you freeze these arguments and let the gradient go to 0, it goes to infinity, the H goes to infinity. And you can assume some bounds. Okay, let's not worry about that. But I put in capital letters there the convex. And that's a puzzling problem because in the periodic case, you don't need convexity. So there is a problem with that, with homogenization of Hamilton-Jacobi equations in random environments. You have to assume convexity. And if any one of you, and the reason is that all of us who have worked on that have the wrong proof. I have this fear that one day someone's going to get up and give a 2-page proof of the non-convex case. So everybody who has worked on that doesn't have the right proof. And so if any of you want to work on that, I make a suggestion. Understand the problem, don't read anything that has been written, and try to do it. Because if you read anything that has been written, you're going to go the wrong direction, the wrong way. All right. The other assumption I want to point out here is that there is no gradient dependence on the A. And that's also a problem, because ultimately what I would like to homogenize is epsilon mean curvature plus oscillatory first order derivative. And that I don't know how to do. And that's a real problem, a real physical problem that is of interest. But if that would have meant that I have to put a gradient there. So two open problems here. A that depends on the gradient, and H that is not convex. Now, if you just stick with the Hamilton-Jacobi equation, then you can do a little bit better. You can do quasi-convex in the sense of level set convexity. So if you have an H that is level set convex, not exactly convex, then you can still homogenize in the case of the Hamilton-Jacobi. All right. Now let me go, all these things are statements. Now here is a fun result, a fun observation. Is there a real difference, qualitative difference between random or periodic? And let's stick with this problem. Remember, I mentioned that I didn't write it. This is a problem you get. All right, so I might as well write this thing down so that. So if I start, let's say, with Vt minus Laplacian V plus V x d0, and I'm interested in the long time behavior. So the thing I'm going to do is I'm going to define V epsilon xt to be Vx over epsilon, t over epsilon times epsilon. Then I will get and if I write V epsilon exponential Z epsilon over epsilon, or U epsilon over epsilon, I get that equation. So I'm around the right problem, right? And now, this problem satisfies the assumptions of the theorems that I flashed for you, because this is a nice uniform elliptic case. There's no gradient dependence. It's as coercive as it can be, and take V bounded. It cannot be any better situation. So homogenization applies. It works. The results I stated earlier work. And they say that as epsilon goes to 0, there is a limit that should satisfy this evolution problem. So u bar t plus h bar of the u bar should be 0, and you start 0. You start at 0, you start 0 here. But it's clear what the solution to that problem is. So the solution of that problem is minus th bar of omega. So we know that if we take that equation there and we homogenize, you converge to minus th bar of omega, where h of 0. I'm sorry, where h bar is the effective Hamiltonian. And you want to know what the question is, what do we know about the h bar at 0? So if we're in the periodic setting, h bar of 0 will be the principal eigenvalue. That's exactly, it's similar to what I said at the beginning about the long time behavior of the semilinear heat equation. So, and the principal eigenvalue is positive. All right? So here now comes the point where I can have either visible or invisible potentials. If I'm in the periodic setting, h bar at 0 is, I said, positive. So the solutions at the limit move with speed h bar of 0.
Your v depends only on x, not on t.
Yes, here's only on x. Yes, absolutely. On the other hand, if I'm in the case of IID, this is not going to happen. If the potential is IID, think about it. IID means that, in that situation, you can think of the following picture, that you can have arbitrarily large areas, and think of a potential to be 0 or 1. Okay, take a 0, 1 potential, and if you are in the IID situation, then with some small probability, you can find arbitrary places, arbitrarily large places where there is no potential. The potential is 0. Okay, that is what I will call invisible potential. So this is what, give me a number, and I can find, with some positive probability, for every arbitrarily large rho, I can find the v is less than alpha. So in that case, there is no potential. You don't homogenize anything, so you're going to go to 0. And IID, Poisson clouds, all these things will do it. And while if periodic doesn't, and periodic is the visible case, I said positive is negative, I mean, I always mess this thing up, because it should be positive, because h bar is the principal eigenvalue. So this is a real difference between periodic and random. This is very much related whether the spectrum of the operator is achieved, whether it's there is an eigenvalue at the bottom of the spectrum or not. So if you are in the random setting, there is no eigenvalue. It's a generalized, yes.
I mean, here what you really want to do is subtract this kind of trivial drift and blow it up until you actually see something.
Absolutely, when it is 0. Yeah. Okay, I understand that.
It's not 0.
No, I understand that. But what I'm trying to, so this is, I would call that, yeah. But what I'm saying is I just, which means you can go further and you can get an extra thing, and that's another story. But at that level, what I want to say is that if you are random, you can have a situation where that's 0, where that is not. I mean, the reason it's important is this. If you homogenize that problem in the periodic case, you get a Hamiltonian that looks like that. While if you homogenize it so that's periodic. While if you homogenize it in the random case, you will get an h bar that looks like that. Okay, and again has to do with whether the bottom of the spectrum is an eigenvalue or not. Okay, now let's go to rates of convergence. And to do rates of convergence, I have to I have to look at this model problem. So this model problem, the result is more general, but I'm just stating it in a simple case. So I'm assuming H is coercive, convex. To simplify things, I make it be 0 at 0. And I'm taking a potential here, which is greater or equal to 0 and bounded. In that case, the effective Hamiltonian will have flat spots. The H bar will look like that. So although you start with a problem that is, it could be uniformly convex, it can be du square, nevertheless you get something that is flat. And we have homogenization, so the u epsilons go to u bar. The u bar will solve that problem, and by uniqueness, u bar has to be minus epsilon h bar of p. All right, so keep that in mind for a minute. Now, it turns out, by the way, that the rate of convergence of the u epsilons to u bar controls everything. If you have a rate by which the u epsilons go to u bar, then you can get a rate on the general homogenization. All right, so in the periodic environments, it turns out that the u epsilon plus h bar has a universal rate. It's like epsilon, because there are correctors in the periodic setting. And therefore, some abstract nonsense tells you that if you have epsilon there, then for the general homogenization, you have epsilon a third in the periodic setting. So periodic homogenization for periodic Hamilton-Jacobi equations, the rate is epsilon a third. Okay? In the other case, the things are more complicated, and you can make it to be arbitrarily slow. So let me state the same assumptions. But now I'm going to remember at this hand-waving transparency, I said if you have some control on the rate of the mixing, then you can get a rate. And the control here is I'm going to assume for this problem, and we don't know how to do anything more than that, we're going to assume that the V of omega is independent of finite range. Yes?
Third is basically the KPZ scaling third.
I don't know whether it's related to that.
It's the same equation, and that's the fluctuations of optimal behavior.
I don't know whether it's, I mean, I believe, but I don't know whether there is any relation. For me, this third, I don't know how to show to you it's optimal. It's, there's only one proof you can do, and that gives you a third. So now I go to the random setting, and the mixing assumption I'm going to make is that at distance d, the potentials become independent. Right? So that I don't know how to do mixing for that. That's the only assumption I can make. And look at the difference. I don't think anybody's going to read this transparency, but remember, I went from a third. Actually, this is, I went for a third, epsilon a third in the periodic case to what the rate is in the random case. So the rate in the random case, one direction is, this is at the level of epsilon. In the periodic case, I had epsilon. Right? The periodic case, I had epsilon. And look what I have here. From below, I have epsilon a third, where I had epsilon in the periodic. In the random one direction, I get always epsilon a third. On the other direction, however, it depends on whether I am near the flat spots or not. So in general, you get a different rate. There's some constants here. And this is a rate for the general homogenization. So the general homogenization was a third. And here you get epsilon a fifth. And from below, you get epsilon to the 1/8. None of these things are sharp. Okay? But definitely, they are not a third. And this is very much related to rates for first passage speculation. And there is a conjecture about what the constant has to be. And we are as far away as you can be from that constant. So there is no reason, I mean, this is like doing a little bit dispersive equations when you try to lower the negative Sobolev exponent for which you have existence. And then...
I'm a little bit confused. I mean, percolation, is a very degenerate case, right?
Yes or no. Percolation is the case where it will look u epsilon t plus, if you like, a of x over epsilon du epsilon. I mean, it fits in the problem. I wrote a special case there.
No, but I mean, the a has to go to 0.
Yeah, but I mean, okay, I can allow v to be unbounded here. Let's not worry about these things. I'm just writing a special case on the problem. I just have to write something down. A can go to 0 there, but then the rates they get, they make assumptions about how a goes to 0. And then you can plug it into the thing. All right. As a matter of fact, the proof we have for that is understanding a little bit the way Kesten and others got the rate of convergence for percolation. All right, so, but I want to point out again this difference. You go from the situation where you have a universal epsilon a third rate to a setting now where the rate is definitely not that. And as a matter of fact, one direction you can make it arbitrarily slow. All right, now let me go to the fully nonlinear case. A fully nonlinear case, there are two kinds of results. Either f is uniformly elliptic, or it can be degenerate elliptic, but you have some expectation bound on the you have an estimate on the p norm of one of the lowest the lower bound of the ellipticity. So here the ellipticity, the problem is elliptic, uniformly elliptic, but the ellipticity constant can go to 0. And if you make such an assumption, then again you can homogenize and you can get a limit. And then if you assume that the media is strongly mixing, let's say at large with a logarithmic rate, then you can prove a logarithmic rate of convergence. So I want to make a few comments here. One is about this rate. So here it looks very sharp. We assume logarithmic, we get logarithmic. Right? I assume logarithmic, I get logarithmic, but I'm writing this to cheat, because even if I assume algebraic, I will get logarithmic. Even I assume IID, our proof is going to give logarithmic. In the linear case, with smooth coefficients, there are results by Urinsky that says if you assume algebraic, you get algebraic. So in the linear case, you have algebraic, linear smooth coefficients, algebraic implies algebraic. In the nonlinear case, IID implies logarithmic, and there is a reason for that. And the reason for that it has to do with following fundamental estimate for linear equations. So L is, let's say, is an IIJ, UXI, UXJ. Okay, that's L. And there are two questions you can ask. Control U by L of U, and control L of U by U. There are two natural questions to ask. So control. The first one is the ABP inequality. ABP. That says up to constants that U sup norm is less than L of U ln. That's the famous ABP inequality. The other comes from, that's ABP. And the other is something less known, which is the Fabes-Struck, that says that, roughly speaking, U in the half ball, I mean, there are assumptions for all these things, huh? Is below by some constant times the L of U in Lm, with M very small. Okay, so that's an estimate from below on U in terms of the L of U. And in the linear case, uniformly, the linear case where with smooth coefficients, of course you don't do that. I mean, what you write down is the fundamental solution. And for the linear case with smooth coefficients, there is a good fundamental solution. You have a good lower bound for it. And therefore, the homogeneity between the upper bound and the lower bound are the same. And therefore, you get algebraic. If you are in the nonlinear case, which is like having Aij with bounded measurable coefficients, then you are forced to use these two estimates. And the fact that one is n and the other is m, which is much smaller, is the reason that in the end you get logarithmic. Because what you want to do is you want to keep chopping your cubes smaller and smaller, and then at some point you are going to have to cut much more to control things. This
Second is for positive substitutions.
excuse me?
The second one is for positive.
It's for positive solutions. The right-hand side has to have a sign, and there are some. I wrote. I mean, there are conditions. The correct thing here is you have also a coefficient that sees the L infinity norm of the L of U. So it's and it's nothing else. The Fabes-Struck is nothing else but a measure theoretic lower bound on the Green's function. So the other point I want to make here is forget the degenerate case. Take the first case, uniformly elliptic. How simple it is. Uniform ellipticity you can homogenize, while in the case of the Hamilton-Jacobi equation, we had to assume convexity, we had to assume all that stuff. And I claim that the homogenization for uniform elliptic, I claim that if you have uniform ellipticity, homogenization in principle is very simple. Because heuristically, if you think about homogenize, the solution has to fill the whole medium. The medium average, the solution has to fill everything. And if you are uniformly elliptic, you have infinite speed of propagation. And therefore, automatically, the solution fills the whole medium. There is not much time not to do it. And one way to see that is let's homogenize in 1D, technically. So now that looks like a tough problem. However, if F is uniformly elliptic, it's invertible. And so that's the same as homogenizing this. Right? So it's a very simple problem. Now let's go to the Hamilton-Jacobi case. You cannot play this trick. There's something else going on. So what's happening in the Hamilton-Jacobi case is that the information somehow is transmitted along, I'll put it in quote, generalized characteristics. They don't exist, but there are some objects like that. And somehow you need to know that you can reach any point within time t. You can go distance t and over in time t, and that's a hard thing. In the periodic, in the convex case, you can write down the variational formula for the solution, so you have real minimizers, and you can control things. In the non-convex case, the picture is much more complicated, and that's where the problem is. Having said that, so the homogenization of that conceptually is more difficult than that. Nevertheless, the proof for this, the homogenization, is a page. The proof of that homogenization is about 30 pages. So although it's simpler, conceptually, it's harder to do it here because you are forced to use some formulas or whatever. It's simpler. Okay. All right, I was planning to show you some things, but yeah, this is not to be read. So I want to go now to the G equation. I mean, I have only 5 minutes. And in spite, I could say that you slow me down by 5 minutes. But your chairman is taller than me, so the chairman is taller than me, so I cannot do that. I have to be concerned about that. Okay. One word about the rates, how the rates come in this game. Again, for someone who discovers it's not how to get rates, but all right, so how do you get rates in these problems? How does mixing help you to get rates or independence? So let's think, what is the homogenization is more or less like the law of large numbers at some place, the ergodic theorem, some law of large numbers. So let's see how we get rates. So let's say we have a family xi of independent random variables. So I will write their expectations as x and vx, the covariance. They're independent. And to get the rate of convergence, you have to find the rate on the ergodic theorem somehow. And so the question is, what is the variance of the average of the xi's? And let's simplify life. Let's make that 0, so I have to write less. Okay, so you write this thing down, you expand it, you use Hölder's inequality of the right spaces, and you see that the variance is decreasing. The variance of the mean is, the average is below the average of each one. Now, so this is like a covariance estimate at the level of the ergodic theorem, because the xi's are just independent random variables, so they are stationary. Now let's make the second thing, let's make them to be IID. Then you do the same calculation, and you realize that you can throw away some terms, because the terms that are like EXI xj by independence are 0. I assuming that the average is, the mean is 0. So if they are independent and I is not j, these are 0. So clearly here you get an estimate which is 1 over n variance of x. Okay. So that says that if it's mixing, then you have some different things. So that's what comes behind all these rates. Now the issue is, how do you reduce yourself in such a thing when you are in the random case? So you need something to localize things. And when you're doing the uniformly elliptic case, the way you prove the result is using the obstacle problem, which localizes things. While in the Hamilton-Jacobi case, you cannot do that. So in the Hamilton-Jacobi case, you have to go to these ideas from percolations, and you have to use one direction, a sophisticated inequality for probability that is called Azuma's inequality, which in my lack of probabilistic knowledge is nothing else but this estimate for semi-martingales. And that's where things become complicated. Okay, now 3 minutes and I finish with the G equation. So the G equation for me, it will be an example of a non-coercive problem. So this is the G equation. If I assume that the size of V is strictly less than 1, then of course the problem is coercive, and everything I said before works and it homogenizes. But if V is bigger than 1, the problem is not coercive, and things can go wrong. And what can go wrong is that the vector field may be large enough to trap points. Okay, so there may be some points that cannot move, because the vector field doesn't let them go out of there. And okay, so that was the example, doesn't matter. So now the question is, what do you do? How do you homogenize? Okay. I will just state the two results, nothing else. Okay, so the first result is what you do in the periodic case. So how do you homogenize the G equation in the periodic case? The X's equation in the periodic case, you can homogenize it. In general, if you make the assumption the divergence of V is less than 1 over the isoperimetric constant. And then you can homogenize, and you can get enhancement. Now, if you go to the random setting, the problem is more complicated because I don't have an isoperimetric inequality. I cannot do what I did before. So here we can still homogenize. Now we have to assume divergence 0. We don't know how to go away from divergence 0, and we can still homogenize, and we can still get enhancement. The reason the problem is difficult here is when I do the right thing and I'm at a place where I can apply the Sabaty-Vergotic theorem, what I have is I violate the integrability condition of the Sabaty-Vergotic theorem. As a matter of fact, we can create a medium. We have an example of a particular medium for which there is no, this thing is not integrable, what you need for the Sabaty-Vergotic theorem. So the way we do that is through the following idea, and I finish, is we shadow the thing that we need to homogenize, or the thing we need to take a long time average. We are shadowing it by something for which we can prove, we can use the ergodic theorem. And once we construct that, so that means we have to construct a particular process for which we can apply the Sabaty-Vergotic theorem. Because we are always nearby, we can homogenize the problem. Okay, so I'm just going to show some possible open problems if they show up. But it will take some time. I was planning to describe all these things in the lecture. And now I think you see the arguments, you understand everything I'm saying. All right, so in summary, this is some problems. And I'm specializing in the case of the viscous Hamilton-Jacobi. Convex or not convex, I hope I explained that well. Dependent gradient. The problem is I want to do this equation here. I want to homogenize epsilon mean curvature plus first order motion. Big issue is oscillatory boundary conditions. That has been recently understood in the periodic case, but in the random case, nothing is known. Here's a trivial, okay, this bracket still misses. A viscous G equation. What happens if I put in the G equation an epsilon Laplacian? And we don't know how to do that. In the periodic case, it's a triviality. In the non-periodic case, in the random case, we don't know. And the proof we have for the problem without a Laplacian is a more ergodic theory proof, so it doesn't give you any estimates. We cannot do that. And the next question, which again is open, and it's as difficult as this one, I think, is to put oscillatory in time vector fields for the G equation for the random case. Okay, I'm sorry I went long. That means Stefan cannot ask any questions. And thank you very much.
Does anybody have a quick question? So I think we already asked quite a few questions during the talk, so let's thank Takis again.